Hey everyone, so let's review where we left off in our last video. So we have this main.py script which is located 2 levels deep under our project root. So we have the scripts directory which is located directly under our repository root. Then we have supernested directory under it, and we have our script under supernested directory. Problem with this hierarchy is when we call main.py script, sys.path has this location referenced in it, but from that location it's not able to find my folder package, which is our top level package, and it's located directly under our repository root. So let's start our terminal and try to replicate that error. Will uv run main.py script, and as you can see, it's not able to find my folder module because it's located 2 levels above where main.py is located, and the first entry in sys.path is that of our script location. Now we circumvented that issue by calling main module instead of script by using python -m package hierarchy of our main module. We can also do this by using uv run command. In that case, we won't even have to activate virtual environment because uv will find it on its own. So using this syntax, we are not calling main.py script, we are calling main module with full package hierarchy. And in this approach, it will be able to find our my folder package and execute code correctly. We also resolve this issue by manually adding the location of my folder package in sys.path, as well as by moving our entire package right next to main.py so it has no difficulty finding it. But all of these ways of resolving this issue are suboptimal and not preferred, especially in production grade Python projects. And this is where uv build comes into picture. So our problem statement here is we have to somehow define our top level package, in this case it's my folder, and its location such that Python is able to find it during runtime without us having to manually edit sys.path or call module instead of script. So let's go to pyproject.toml file and add a couple of lines of new configuration here. So we'll add build system to be uv build, and you can also define version here if you want. For now, I won't define any versions here. Then build backend that we are using is again uv build. In fact, let me also define version here. Otherwise, there is no point of adding requires. So let me find what version my uv has. 0.9.13, so I can just add should be greater than equal to 0.9.13. Now let's uv run our script and see what happens. It still will give us an error, but it will be a different error. Now right off the bat, you can notice that this time around uv is trying to do something which it wasn't previously when we did not have this build configuration in our toml file. It's trying to build our project packaging study, but it failed, and the error here I think is quite descriptive. So uv is telling us that because we have this configuration, it's trying to build this package, but it has some default expectation in terms of package hierarchy. It's expecting for there to be an src folder under our project root, and under it there should be this top level package packaging study with an init.py file, and because it's not able to find it, it's throwing an error. Now we can change this default configuration again by adding some more configurations in our toml file, and I'll show you how to do that in this video later. But for now, let's change our project hierarchy to match uv's default expectation. We will create an src folder under our project root. We will move my folder under it, and we'll rename my folder to have the same name as our overall project, which is packaging study. And by the way, this expectation of our top level package name, it comes from our pyproject.toml configuration. So we have defined our project name to be packaging-study, and in this case, if we have hyphens in our project name, then uv will automatically convert it into underscore, but it will keep top level package expectation the same as our package name in pyproject.toml file. So now we have src folder and we have packaging study as our top level package. uv will build this successfully. Let us rerun our script. It still won't run because now we have to change our import statements also, but let us see what uv does. So as you can see, it was able to successfully build top level package, and especially notice sys.path. It has a change now. So obviously its first entry is script location, then it has base Python locations, and it has our virtual environment locations. But what is different this time around is the last entry in sys.path is that of our src folder, or it's the location of top level package packaging study. And this is essentially what uv does the moment we add this build configuration. what UV does under the hood is it looks at our project hierarchy with a certain expectation that there should be an SRC folder, and under it there should be a top level package with the same name as that of our project, and that is the location which UV appends to sys.path. And therefore now we can ensure that main.py correctly imports our package. Even if we make a script call, all we have to do is we have to now account for our top level package name, which is packaging study and not my folder. This statement will work just fine because we have this location where our package is located. So we don't have to use module call. We don't have to manually change sys.path. UV build will take care of making sure that our top level package location is always part of our module search path. So Python will always have an access to it. If we try to run this code now, so as you can see, it's working now. What's important to remember that the most important change that UV made in order to make this work is by adding our top level package location in sys.path. So this way we now don't have to rely on relative import. So we might further nest our main.py file. So we can create another folder here, super duper nested, and we can move our main.py file inside it. Even after moving our main.py file one level below what it was previously, we still don't have to make any changes to our import statement because top level package location has not changed. It is still under SRC folder, and therefore even after further nesting our main.py file, our code will, hang on, what happened? Oh right, of course, I have to now change the location of our script call. So it's super duper nested folder now, and it runs just fine. And this is the most optimal way of handling imports in a project which has fair amount of nesting and is sufficiently complicated, is just define UV build configuration and use absolute imports instead of relative imports, and our absolute import paths will begin from our top level package downwards. Now this default package discovery expectation that UV has, where it expects there to be an SRC folder under our project root and a certain package name which matches the name we have in our pyproject.toml name, we can change one or both of this by adding configurations in our pyproject.toml file. So I'll change the name of my top level package to my top level package, and then I'll change my import statement to reflect that change. This alone will work just fine because all we have done is we have changed top level package name, but we still have SRC folder. And if you remember, when we ran our main.py file, it added this SRC location in sys.path. Python will still be able to find our top level package and will be able to correctly interpret our import statement. But where it will start failing is if we change the name of our SRC folder. So let's change that to some other folder. Now in this case, our script run will fail. It's telling us that it has a certain default expectation of project hierarchy which is not being met. This we can override by adding tool.uv.buildBackend, and then we define our module root to be some other folder. That is the root folder that contains our functional logic in my top level package. If we run our script now, it will still fail, and we'll see what the error tells us. As you can see in the error, we were able to override UV's expectation that instead of finding SRC, it should find some other folder by this configuration in our toml file. But it's still expecting our top level package to be packaging study. And that is where we now have to also add another configuration here, and that will be module name. And our top level module name is my top level package. Now let's rerun the script. So as you can see, it was able to successfully build our project with new expectations that our folder instead of SRC is some other folder, and our top level package under it is my top level package instead of packaging study. Let's revert the names of these folders to what UV expects by default. So I'll rename some other folder to SRC, and I'll rename my top level package to be packaging study. Now obviously, now if I try to run it, UV will not be able to build our project because we are telling it something different in our configuration file than what exists in our project hierarchy. So again, it's telling us that it's expecting some other folder, my top level package init.py, and obviously we don't have that. So here we can either get rid of this configuration because this is what UV expects by default, but I always like to have my configurations explicit even though UV expects it. So I'll have my module root to be SRC, and I'll have my top level package to be packaging study, and I'll change my import statements to reflect that, and just confirming by running our script, and it will end up being packaged successfully with successful script run. Now the layout that we have been working with so far is called as SRC layout. Now there are broadly two different kinds of layouts in Python. One is SRC, which is what we have here, where our functional logic or our top level package is located under a folder SRC instead of being directly located under project root. But we can also place this top level package directly under project root. So we can move this directly under our repository root. So now our top level package is not nested inside SRC folder. Obviously, if we run it now, it will fail because we have our module root defined to be at SRC and it's trying to find a packaging study under SRC, but no such module exists. So in this case, we will keep our module root to be an empty string. So this essentially means start looking for the module from repository root itself, which is where our top level package is located. And running this will run just fine. Now this layout is what is called as flat layout as opposed to SRC layout. And Python has a good explanation on this. I'll link this in the description where it explains at a high level the difference. So here our top level package or functional logic is directly located under project root. And this is the SRC layout which we had previously, where it is nested inside SRC folder instead of being directly located under project root. Mostly in production grade projects, we tend to prefer SRC layout because it segregates our functional logic and packages inside a nested folder. And because of that, you will end up catching a lot of import related issues early in your development. Whereas in the flat layout, it's much more likely that your import issues will not show up in the development and everything will be working fine when you try to run your code during development phase, but they will end up showing either in deployment or even worse in production. So again, by default, always prefer SRC layout unless you have a good reason not to. So let's go back to our project and move packaging study to SRC folder. Change our module root to be SRC folder from empty string and just confirm by rerunning main.py that it's working fine. So I'll end this video by discussing absolute imports versus relative imports and when to use which one. So if you remember, we have already used relative imports and we have not gotten rid of them. Even after defining our top level package hierarchy using build configuration, we are still using relative imports here, for example, where we have under our packaging study 3 modules: calc.py, otherops.py, thirdops.py, and we are importing respective functions from those 3 modules. And because of this statement in our init.py file, we are able to use this particular import statement where we are importing from packaging study all these functions. Because what happens when we call the import statement from packaging study for the first time is our packaging study is initialized by init.py file and all of this import statements are run, allowing us to directly import functions. But we could have also explicitly imported them by using absolute paths. So for example, we could have used this import statements because now we can run absolute import statements beginning with packaging study as our top level package. So just to confirm that this will also work, we can run main.py and as you can see, it's successfully run. But obviously in this case, it makes sense to have simplified import statements, which is why our earliest import statement where we were importing those functions, leveraging our relative imports in init.py under packaging study, that was a much simplified and elegant approach. So we are calling absolute import from our top level package combined with relative imports in the init.py file. And this is usually how I like to combine absolute and relative imports. Within local packages, I like to have relative import statements in init.py file, and the higher I go in the project or package hierarchy, the more I like to use absolute imports. As well as whenever we are calling a script, that is also the place where I like to use absolute imports. In fact, our relative imports will simply not work in this scenario unless we use one of those hacky ways that we used in the last video. Just to drive home this point a bit more, I'll create some sub packages within our top level package. Let me create calc package and I'll move my calc.py file under it. I will create init.py file here and I'll end up importing my functions relatively inside that init.py file under calc package. I'll create another sub package for these 2 modules, other ops and third ops. So I'll create misc package. I'm running out of names, and move this to Python modules under it. And as usual, I'll explicitly declare it as a package by creating init.py file. And here I will be calling this to relative import statements. So within our sub packages, calc and misc package, we have relative import statements importing functions from the modules which are under those packages. And I can still use relative import statement to import those functions into our init.py file, which is located under packaging study package. So here we will import relatively from our calc package respective functions, and from our misc package those two functions. Now let's go ahead and run our main.py file. We don't have to change anything in our main.py file because we are still importing from our top level package packaging study, and all of this import functions, they already exist in our relative import statements here in the init.py file directly under packaging study. So while we had to change a few things in our init.py files, we still don't have to change anything in our main.py file, and this import statement will end up working. And let's run our script. And as you can see, it's run successfully. Now, there are different ways to approach this choice, whether to use relative imports or absolute imports. One of the rules of thumb that I use is anytime I find myself using multiple dots, right? So if I have to climb one level up in this case, where instead of using dot, I have to use dot dot or dot dot dot, and I've seen projects where people have used like 4 or 5, 6 dots. I generally use absolute imports. It's only within very localized package hierarchy where I can get away by using a single dot or at most 2 dots is when I tend to use relative imports to simplify my overall absolute import. So basically just avoid having multiple dots when you're trying to relatively import something in your module. Another choice that we can make is in terms of how much to consolidate and simplify our import statement. For example, in this case, we have imported all the functions by running one import statement. But for some reason, if we want to differentiate between what we are importing from our calc package versus misc package, then we can go to our init.py file under packaging study and just get rid of this two statement. We don't need them. Instead of importing everything at once, we can then segregate our import statement in terms of what we are importing from calc package and importing from misc package. These kinds of choices are important because if you have a new developer, for example, or if you have a person who has never worked with this code, looking at this code, then we want to make sure that our import statements are not so complicated that they don't understand the project hierarchy. So they should be able to understand where these functions are coming from and then to find the respective packages and modules in order to debug or look at that functions. In this case, perhaps it makes more sense to just have separate import statements for what we are importing from calc package versus what we are importing from misc package. And this also will work. So let's confirm that part by UV running our main.py script. Okay, and as you can see, it's running correctly. So that's it for this video. In the next video, we'll discuss what actually is happening under the hood when we add this UV build configuration. So we kind of discussed at a very high level that by adding this configuration, we are asking UV to add this top level package path to our sys.path. Okay, so it can find our top level package and we can use absolute import statements beginning with our top level package. But UV is doing a lot more than that under the hood, and it has to do with something called editable installation. We'll discuss that part in the next video. What is editable installation and what is the difference between editable and non-editable installation. So thanks for watching this.